talk about measures of spread and the normal distribution. So, measures of spread describe how data are spread out around the measure, our central measure. So variance is a measure of spread around the mean. So it's the sum of the squared differences. It's essentially the average squared deviation, where xi is each individual value and mu is our measure of the center, our central spread. So to remind you all, sigma is that Greek letter with the little poof curl. That's our population value. Those are not estimates. Those are true values. While S is our sample. Now, so variance is an unstandardized version where everything is in squared units, versus our standard deviation is the square root of it. It gives us kind of the average deviation from the mean. Now, this is not your intro stats class, but just as a reminder, when you are adjusting for sample size and essentially degrees of freedom, you need to use n-1, not n. Otherwise, your estimate is biased. So in general, here are the basic properties. Standard deviation is in raw score units, while variance is in squared units. So square feet versus feet. Now, both variance and standard deviation are highly not robust. They are highly sensitive to outliers. Now, if we were in class, I would ask you all why, and sit here awkwardly until someone answered and just revel in the discomfort. But if I did that, I would be here forever because I'm recording from my apartment. So I'll tell you. Oh, shit. Okay, sorry. They're less robust because the difference between the individual value and our average is magnified. It's squared. So if there is a huge outlier that's way out there, instead of it just pulling on it like once, like we have with a mean, that difference is squared, making it even more influential. All right, so normal distribution. It's a particular bell-shaped curve that has the following really nice math properties. It has two parameters, mu, pronounced like the Pokemon, and sigma, which is pronounced like the Greek letter. Now, the standard normal simplifies that equation to this really nice number. If you plug in mu is 1, or mu is 0, and sigma is 1, this equation gets drastically simplified. And we tend to like simplifications in statistics as much as possible. Now, general properties of the standard normal. The mean is located at the center of the symmetric curve, and it's the same as the median. Changing mu without changing sigma moves your data along the normal curve without changing the variability. So it just shifts. Now, standard deviation, sigma, controls the variability of a normal curve. So when the standard deviation is larger, the area under the curve is less concentrated. They have the same area, so that white space is the same, but for high variability, it's spread out. It's like smooshed like a pancake. And the standard deviation actually is the distance from the curve at the change of curvature. It's that change of that inflection point of either side, which is kind of cool. But why am I telling you all this? So the standard normal is a model of the real world. It's not exact, but it's a really nice model for a lot of things. Physical features, psychological features, performance variables. Not all variables follow the shape. Like there are skewed things like income, any count variable like number of kids, number of questions missed on an exam. But overall, it does a lot of things well. It describes a lot of things. Now, to illustrate, I have plotted a histogram using height data that Galton collected. Now, this is overlaid with a standard normal, so you can see it's not perfect, but it's pretty good. You know, it's got that nice belly-shaped bell curve. And, yeah. Pester me if you want the R code. I might upload it. Pester's not the right word, but you know what I mean. All right, so the area under the normal are informative. So, like, the normal is a model of the real world. Again, it's not exact. Oh, these are my notes from the last slide. Oops. Okay, so here are some... Whoa, that's broken. Weird. Okay. Sorry. So, in the normal distribution, here are some key percentages and rules to know. So, one standard deviation to either side, so one standard deviation out, captures 68% of everybody. So, that's 68% of the area. Two standard deviations out on both directions gives us 95%. 3 captures 99.7%. Now that's on both sides. So if you want to just look at average to above, that only captures 34%. But, so that's the idea. Now you've hopefully learned a lot of these tricks already, but I'm going to review them. The normal distribution is symmetric, so you can kind of flip the area. 50% of this area is above 0, 50% is below. The total proportion is 1 or 100%. Now, you can use a couple of these tricks, and I'll show you in a second, to find like unlisted areas if you have to like use a z-score table, because those still exist. I have quite a few. Or if R is unavailable to you. Areas are both additive and subtractive, so you can find different chunks by being essentially clever. So to illustrate, here I have the distribution of an Iowa test of basic skills. It's a vocabulary score for 7th graders from Gary, Indiana. And it's pretty close to normal. Now suppose that we have a distribution of 6.84 with a standard deviation of 1.55. We can sketch the normal density curve for this distribution as I have done here. Now ask yourself, what percentage of those scores fall between 3.74 versus to 9.94? And then what percentage of the scores are above 5.23? You can either pause here and do the exercise for yourself, or, and I can show you, about 95% of our scores are so the red scribble out captures the ITBS score between 3.7-ish and 9.9-ish. Versus for our last little piece here. So here we can see that only 2.5% of our data are below this number, which means 1 minus 2.5% is how much of our distribution is above that number. So, yeah. So that's wrapping up measures of spread and the normal distribution. I will be embedding a few videos or making it a separate module. I have not decided yet to show you how to do it in R. And this is where I would say, congratulations, we did it in R. Cool. I think I'm going to cut here because I would like to eat my pizza.